Greetings. Today our video is going to be a little bit on sound, some things you want to know. We'll do some frequency range, but a lot of our time is going to be spent with the speed of sound. Okay, so first thing you want to know is the type of wave that sound is. That would be a longitudinal. So if you've ever seen a speaker, especially a woofer, subwoofer, you can see it goes in and out. It's pushing on the air and pulling back on the air. That pushing on the air will cause a compression followed by pulling on it, which is a rarefaction. And so that is a compression wave. Compression rarefaction, that's a longitudinal type wave. Really kind of hard to draw, but usually when we still draw the waves, we draw them as if they're transverse waves, but we really mean that they are longitudinal wave. The frequency range for human hearing is, roughly speaking, from about 20 hertz on the low end to about 20,000 hertz on the high end. Okay, that's an average. That's for humans. If you're something below that, that's what you hear with your ears. You could still feel things with your skin if you've gone to a concert and you feel that bass really pounding on you. You can feel that with your skin. But in terms of your hearing, typically 20 to 20,000. If you're something below that, that's often referred to as infrasound. If you're something above 20,000, that would be ultrasound. Something above that you can't hear. Some animals can hear in a slightly different range, and so you might have dogs and cats can hear things that are above 20,000. Now, even though humans typically are 20 to 20,000, as you get older, you will lose some of that higher frequency range. Some of you may be hearing impaired, and people who are hearing impaired, a lot of times they don't necessarily lose hearing all over. It might be in certain frequency range, and could be just your biology. It could be trauma that you've occurred, could be overuse of listening to loud music, especially like with earbuds at close range. A lot of things that can cause hearing damage, pardon me. So now, some things you may want to consider as you look at and study. You may want to find some things in the physics classroom. Here's a page that has a lot of different things that you can, if you're interested, even beyond what we're going to be talking about. But here I want to start with a little bit on the sound, using a sound generator. Here's an online tone generator, so we can hear a sound. And there we're at 235 hertz, but we can change that. We can go down. We can go up. Now, speakers, especially on computers, may not be very responsive at the low end. So even though you may not be able to hear really down low, if I had a regular speaker, you might be able to hear that. But and if you're up the amplitude high enough, in some cases you can hear it. Me personally, this region here sounds extremely loud in that 2,000 to 5,000 hertz range. It seems rather loud. It doesn't mean it is louder. It might just mean that I am more sensitive in that region. At the very high end, I personally can't hear up there. So I'll show you where I lose it. I don't hear any change in this region. You may be hearing that change right now, but when I get above 12,000 hertz, I really can't hear that. Okay, it's simply not there. You may be hearing it right now. It may even be bothering you, but I can't tell because I can't hear it. That might be the fact that I'm old. It might be the fact of a certain job I had many years ago that maybe did some damage to my hearing. Okay. Now, we'd like to look at the speed of sound. That's really the bulk of what we want to look at today, is the speed of sound. We've been using a lot of 340 meters per second. One thing you want to keep in mind is, although we know that the speed can be measured by distance over time, and we can use the equation f lambda to find the speed, D, T, F, and lambda, they do not determine the speed of sound. The speed of sound is determined by the medium. Okay, that's what's important. Okay. Now, we could get into, since we're talking about gas, in particular air, which is mostly nitrogen and 80% nitrogen, 20% oxygen, which are both diatomic, we can get into all the physics, or if you want to talk chemistry of gases, and talk about many of those characteristics. But I'm going to simplify it for you, and we're going to use this equation that the speed of sound we can calculate. Speed of sound in air is going to be 331 meters per second plus 0.6 times the temperature in Celsius. Okay, so if we simply realize that if you put in 0 for that temperature, then it's just 331 meters per second. The speed of sound increases, speed of sound in air increases as the temperature goes up. As the temperature goes down, the speed of sound decreases. Okay? So with that in mind, we're simply going to do some calculations, and I'll show you how to use that. We're simply going to be using this equation. You're going to be doing two things. You're going to be finding the speed of sound, and you can also use the speed of sound as, in essence, a thermometer. So here's a couple examples. Let's say, for example, you have a temperature of 30 degrees Celsius. What would the speed of sound be? Well, to find the speed of sound, we would take 331, and we would add to that 0.6 times 30. Well, 0.6 times 30 is 18 plus 331. That's going to give you 349 meters per second. Okay. Let's say you had a negative temperature. It's a real cold day, negative 5 degrees Celsius. We would then have 331 plus 0.6 times a negative 5. Well, 0.6 times negative 5 is a negative 3. 331 plus a negative 3 would be 328 meters per second. Well, let's look at the other direction. Let's say that you know the speed of sound. You know the speed of sound is 325 meters per second. Well, what would the temperature be? Well, in this case, what we can simply do is we can simply say, well, the velocity is 331 plus 0.6 times the temperature. So what we're going to do is we're going to take the velocity minus 331, and we're going to divide it by 0.6, and that's going to give you the temperature. So in this particular case, we would have 325 minus 331 divided by 0.6, and you will get, on the top, you would get a negative 6 divided by 0.6, and this would give you a negative 10 degrees Celsius. And recognize it's less than 331, so that would be a negative temperature. Let's say that we had, we often see a lot of 340. A lot of the problems we had done prior were using 340. What does that assume the temperature to be? Well, that would be 340 minus 331 divided by 0.6. That would give you 9 over 0.6, or a 15 degrees Celsius, okay? Which is around 59 degrees Fahrenheit, by the way. So that's why it's that's often used 340. Room temperature is somewhere around, typically standard 72 degrees Fahrenheit, which is, say, around 22 degrees Celsius, which is going to put you up in the 342, 343 range. So a lot of times we use 340, but if you want to be more precise, you will use this equation to find the speed of sound in air. Hope that helps you out. Have a good day.